Hi, this is week 19 of AP Physics, and we'll be wrapping up Unit 6, which deals with simple harmonic motion. For our agenda, we'll be working with part 3 and 4 of simple harmonic motion, which means we're just going to be looking at problems on movement of a pendulum or a card attached to a spring. For our lesson objective, we'll still be using Hooke's law to solve these problems, and we'll also be looking at springs as well and pendulums. So we begin with problem number 10. In this one, it says, a cart oscillates on a horizontal spring. A blob of clay is dropped on the cart and sticks. Explain what happens to the following: to the period, the total energy, the amplitude, and the speed. Alright, so here's our visual. So we have our cart oscillating back and forth. And as it does, a blob of clay goes ahead and lands on it, it sticks. So for letter A, what happens to the period? The period is the amount of time it takes to go back and forth. Now it's going to go ahead and be heavier, so what's going to happen is the period is going to go ahead and take longer to go back and forth. So you're going to say it would increase, the period would increase. It's going to take longer to go back and forth because we increase the mass. Now the total energy would also increase because we have more mass, so therefore we have more energy. It would increase the amount of kinetic energy. The amplitude would go ahead and remain constant. It will still be oscillating between A and positive A and negative A back and forth. The amplitude would not be changed by the change in mass of the cart and the clay. And finally, the speed. The speed would decrease. That's going to go ahead and decrease. We're going to go ahead and go slower because it has more mass, and you can also see that because the period also went longer and it's the same distance, so therefore it's got to be traveling at a lower velocity. So those are the answers for part A, B, C, and D of problem number 10. Let's go ahead and take a look at problem 11. It says an object is in simple harmonic motion, so going back and forth. Of the following quantities related to the object, which of set of 3 can have the maximum magnitude at the same instant? Alright, so the answer for this one, let's see. It will be displacement, velocity, acceleration, kinetic energy, and potential energy. Which 3 could be at the same instant, could be at the greatest value? The answer would be, let's say for a cart oscillating back and forth, let's forget about the clay for a bit. When it reaches the highest amplitude, it will have the highest acceleration, the furthest displacement, and the spring will be compressed, so it's going to have the highest potential energy. So those 3 could occur when it is here. When the cart is here back at 0, it's going to be traveling the fastest without kinetic energy, but the displacement will be small, will have no acceleration, the spring will not be compressed. So the answer would have to be when you have 1, 3, and 5. Displacement, acceleration, potential energy when it's furthest from the equilibrium point. So for that one, 1, 3, and 5, that will be letter C. So that's the answer for problem number 11. In problem number 12, they ask you, you have 3 different experiments, and they're being conducted that pertain to the oscillation motion of a pendulum. So you have a pendulum swinging back and forth. For each experiment, the length of the pendulum and the mass of the pendulum are indicated. In all experiments, the pendulum is released from the same angle with respect to the vertical. Alright, so now they continue. And it says, the pendulum in experiment 2 right here is released from rest at an angle of theta O with respect to the vertical. What is the magnitude of the change in kinetic energy of the pendulum from its lowest point to the highest point in the arc? Alright, so let's go ahead and take a look at that from the lowest point to the highest point in the arc for this one. So there's my equilibrium point. Here we go. There's our angle right here, theta O. And the mass of this, it is 2m, and the length, it is just L. And from the lowest point to the highest point, again, the question is, what is the change in kinetic energy from the lowest to the highest point? So we're solving for our kinetic energy. Alright, so what are we going to do to solve for this one, kinetic energy? Well, kinetic energy, we're going to go ahead and use the law of conservation of mechanical energy to go ahead and solve this problem. Alright, so for law of mechanical energy, let's see, it's going to be mechanical energy initial is equal to mechanical energy final. All right, mechanical energy is kinetic energy initial plus potential energy due to gravity initial, which is equal to kinetic energy final plus potential energy due to gravity final. At the lowest point, which will be here, you could say it's got no potential energy due to gravity because it's at the lowest point. It does have it here. At the very beginning, it's got no initial velocity, so kinetic energy initial would not be there. So for our kinetic energy final would match, it would have to be the same as the change in gravitational potential energy. So which is mass times gravity times height initial. Alright, and that's going to give us our kinetic energy, or change in kinetic energy. Alright, so kinetic energy final is 0, so we can go ahead and have that be changing kinetic energy here. Alright, mass. The mass, they told us it was 2m, so 2 capital M. G is the same. Height initial. How tall is this? That's the one we're looking for. How much height did we change from here to there? By the way, this pendulum, from here to there is the same thing as here to there. There's our angle. So we need to figure out what is the length of this portion right here. So I'm going to draw it in red. I'm going to go ahead and use a little bit of math to go ahead and solve for the length of this red line that I just drew. Once I have it, I can go ahead and figure out this length right there. That's my height, so I need that value right there. Alright, so how am I going to figure out the length of that red line right here? Well, it is adjacent to our angle, and we know the hypothesis. So adjacent or hypotenuse, that's cosine. So it's going to go ahead and be cosine of theta. It's equal to adjacent, which is that red line. I'm just going to go ahead and put it as, let me just call it y, over the hypotenuse, which is L. So I'm going to go ahead and multiply both sides by L. Cosine theta is equal to y. Alright, now what is this height right here? The height is really length minus y. So for the height is really length, this from here to there minus the y, and that will give us this value, which is the height. Alright, I'm going to go ahead and substitute what is y? Y is cosine L times cosine theta, so my height is really L minus L cosine theta. I'm going to substitute that into my formula right here. L minus L cosine theta, and that's going to give us our kinetic energy final, which is also our change in kinetic energy. So there is our formula, and if you look at that, that goes ahead and matches letter D. Alright, that takes care of problem number 12. In problem 13, we're asked the following. It says, a block on a horizontal surface is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall where there is negligible friction between the block and the horizontal surface. The block spring system is placed into a simple harmonic motion. The figure shows a graph of velocity of the block as a function of time. So there's a graph, there's velocity, there's a time. It says, at which of the following times does the block spring system have a maximum spring potential energy? Alright, the maximum potential energy is going to be when the spring is compressed the most. At that point, picture the block going back and forth, or either when it's compressed or stretched the most, but let's go with compressed. What's happening to the velocity? At that point it is changing, so you're looking really at velocity when it's 0. When it is going from left now to right, that is when the spring is now compressed the most. So velocity 0, so it would be at 1 second. It would also be at 2 seconds, 3 seconds, and at 4 seconds. Alright, so of the choices given to us right here, 2 would be one of the answers. Everything else is not there. Another possible answer is should be 1, 2, 3, or 4. Only 2 is listed, so our answer is letter B, 2 seconds. In problem 14 says, one end of a string is attached to an object of mass m, and the other end of the string secured so that the object is at rest as it hangs from the string. When the object is raised to a height above the lowest point and released from rest, the object undergoes simple harmonic motion. There's 3 possible positions for the pendulum x, y, and z are shown in the figure. Which of the following claims is correct regarding the mechanical energy of the pendulum? So here it goes going back and forth, x, y, and z, X and C may not be the same. It says A, the magnitude of the change in gravitational potential energy from point X to point Y is the same as from point Y to point Z. Let's go ahead and take a look at that. And yeah, if these are the points of maximum amplitude, then yeah, that would be correct. The change in mechanical energy will be greatest from here to there as it is from there to there, and they'll be equal to each other. So the answer A would be correct. Let's take a look at B. It says the pendulum has half of its maximum speed whenever it is at a vertical position that is halfway between point X and point Y. Alright, and half of its speed? No, it would not have half of its speed. Letter C, a pendulum with twice the mass would have twice the speed. No, the mass does not affect the swinging of a pendulum. Letter D, a pendulum that is released from an angular amplitude that is twice that is shown will have the same. No. Alright, the angle at which is released, it's irrelevant, so it does not play a role. So the answer for this one will be A. Let's go ahead and move along to our next problem. Problem 15, and this problem says a 0.5 kilogram pendulum bob is raised to 1 meter above the floor, as shown right here. The bob is released from rest. When the bob is 0.8 meters above the floor, its speed is most nearly which of these? Alright, so let's go ahead and solve this problem. Alright, so initial height of this one was 1 meter. Final height of this problem is going to be 0.8 meters. Alright, that's given to us as well. And they want to know what is its velocity when it goes from 0.1 to 0.8. The mass is given to us as well. It is 0.5 kilograms. It's the mass of the bob. Alright, and again, they want to know what is its final velocity. Velocity initial, we can assume that it is 0. Final velocity is going to be question mark. That's what we're solving for. So we're going to use law of conservation of mechanical energy to go ahead and solve for this problem. Mechanical energy initial is equal to mechanical energy final. For mechanical energy, that is kinetic energy plus potential energy due to gravity here. So I'm going to go ahead and put that. Kinetic energy initial plus initial gravitational potential energy. Kinetic energy final is equal plus gravitational energy final. Alright, the only one we can cancel out here is kinetic energy initial because we're assuming initial velocity is 0. But we do have an initial height and the final height. Now we're looking for kinetic energy because that's what's going to give us the velocity. So what I'm going to go ahead and do is I'm going to move this over here. So that's an addition, so I'm going to subtract. So it'll end up like this. Gravitational potential initial minus gravitational potential final is equal to kinetic energy final. Let's go ahead and put in the formulas for it. Gravitational potential energy is mass times gravity times height. So it's going to be mass times gravity times height initial minus mass times gravity times height final. It's equal to 1/2 mass times velocity final square. That is what we're looking for. Alright, we can go ahead and simplify this a little bit. Notice that we have mass on everything. We're going to get rid of it, but not yet. Let me factor out mass times gravity here. Mass times gravity. And I have height initial minus height final. It's going to go ahead and give us the kinetic energy. Alright, so let's go ahead and get rid of the mass. So we have gravity, height initial minus height final. It's equal to 1/2 mass. Oops, no, we cancel out the mass by dividing by mass on both sides. Velocity final square. I want to multiply both sides by 2 to get rid of the half. So I have 2 times gravity times height initial minus height final. It's equal to velocity final square. And at the end, I'm going to go ahead and square root both sides so I can have velocity final isolated. So it's going to be square root of 2 times gravity times height initial minus height final. And that's going to go ahead and give us our final velocity. Alright, let's go ahead and plug in the values. For that one, velocity final is going to be 2 times gravity, which is 10 meters per second squared. Multiply times height initial, which is 1 meter. Minus height final, 0.8 meters. Square root all of that. And that's going to give us our final answer. So that's going to be, let's see, 1 minus 0.8. This gives 0.2 times 10 times 2. Square root of that answer is 2 meters per second. So the answer for this problem is letter C. that brings us to the end of week 19 of AP Physics. Also brings us to the end of Unit 6, which is simple harmonic motion. Thank you so much for watching.